We will introduce several dimension reduction technology in the following. The first, the first one is the principal component analysis, or we call it PCA in short. This is one of the most important dimension reduction technologies, and it's widely used in dimensionality reduction, lossy data compression, feature extraction, or data visualization. And the PCA is also known as the KL transform. And to derive the mathematical definition of PCA, we can view the goal of PCA from two different viewpoints. The first one is we want to find the orthogonal projection of the data onto a lower dimensional linear space such that the variance of the projected data is maximized. So the first viewpoint is called the maximized variance viewpoint. The second viewpoint is we want to find a linear projection that minimizes the average projection cost. Okay, minimize the projection cost. So both these two viewpoints can derive the same mathematical definition of PCA. So on the right side, we can see an example. The red dots are original data point. We want to find a vector such that the projected data in green, the projected data have maximum variance. Or we can see that we want to minimize the projection cost. So the blue line here denote the projection cost. We want to minimize the error between the original data point and the projected data point. Okay, so we can view the PCA from two different perspectives. So let's start from the first perspective, maximum variance. So given a data set, so we have a data set xn here, and assume that the dimension is d. The goal is to project the data onto a space having dimensionality m, which m is less than d, and assume that the value m is given. So let's begin with m is equal to 1. So we want to project the data onto a line in a d-dimensional space. So the original data points are d-dimensional. We want to find a line that is inside this d-dimensional space such that we can project all the data points onto this line. Okay, and the direction of the line is denoted by a d-dimensional vectors u1. So we want to find the best vector u1 that represent the line. And each data point xn is then projected onto a scalar value u1 transpose xn. So this is the projection value. Why is the, you can see that actually this is the inner product of two vectors. The first vector is u1, which is the direction of the line. The second vector is xn, that is the original data point. So when we say we want to project the original data point onto a line, we simply take the inner product between them. Why? So let's go back to linear algebra. So this slide is from linear algebra class. So let's recap that when we want to project a vector u onto another vector a, so how can we do that? Okay, so the projection u on a is the inner product between u and a divided by the norm of the square of the norm of vector a, and then multiply a. So this is projection u on a. And the length of the projection U on A is simply take the norm of this vector, and then we can get that is equal to the inner product between U and A, and then take absolute value and then divide it by the norm of the vector A. And this is actually equal to the norm of U multiplied by cosine theta, which the theta is the include angle between U and A. So that's what we have learned from linear algebra. So that's why when we say we want to take the projection of the original data point onto some specific vector, we take the inner product between these two vectors. So this is why. And because we want to maximize the variance of the low dimensional data point, the projected dimensional data point, so we need to take the mean of the projected data. So here we first calculate the mean vector of the original data point. So here is the summation of all data point divided by n. So we get the high dimensional mean data point, mean data vector. And then we project this mean data vector onto the low dimensional space. So this is the mean of the projected data. Okay, because these are all linear transformation. So we can calculate the mean first and then do the projection, which is equal to we project all data and take mean. That is totally the same. And then we can calculate the variance of the projected data. It is given by this equation. So we can see that this is the each projected data, and this is the projected mean data. And then we, just as we have learned from statistics, this is the formula of variance. And then we can represent this value as U1 transpose multiply S and multiply U1, where S is a covariance matrix defined by this. Okay, so these two equation is totally the same. Okay, we just simply represent it as a matrix form, where the matrix S is the covariance matrix. So the goal is we want to maximize the projected variance U1 transpose as U1 with respect to U1, which is a unit vector. So we want to enforce the projected vector U1 would be a unit vector. So the norm of this U1 is equal to 1. So this is also why we say that the projection of U on A, or the projection of X on U, is simply U1 transpose X. Originally, when we learned from the linear algebra, we will take something like we should divide it by the norm of U1. But right now, because we enforce U1 as a unit vector, so the denominator is equal to 1. So we just ignore the denominator in previous slides. Okay, so this is an optimization problem. We want to maximize this with this constraint. And we can use Lagrange multiplier to solve this optimization problem. Lagrange multiplier is an efficient way for us to find optimal solution. And we will not go into the detail of Lagrange multiplier. If you are interested in optimization technology, you may take my another class, Introduction to Optimization, in another semester. But by the way, anyway, based on the Lagrange multiplier, we want to solve this objective function. So this is the original objective function plus by this is called Lagrange multiplier by this this value. And by setting the derivative with respect to u1 equal to 0, so we take the partial derivative with respect to u1 and then set it to 0, we can solve the optimal solution. And then finally, after some mathematical derivation, we can get that the best U1 has this characteristic. SU1 is equal to lambda 1 U1. So this is a form we should be very familiar, because this is the eigenvalue and the eigenvector form. So we see that from linear algebra, we say that AX is equal to lambda X. We say that lambda is the matrix A's eigenvalue, and X is matrix A's eigenvector. So similarly, U1 here must be the eigenvector of S. Okay, and the variance will be maximized if we set U1 equal to the eigenvector having the largest eigenvalue, lambda 1, so that we can get the largest variance. Okay, so if we set U1 as the eigenvector having the largest eigenvalue, we can get maximum variance. So the optimal linear projection for which the variance of the projected data is maximized is now defined by m eigenvectors u1 to um. So in previous slides, we just set m is equal to 1. That means we want to project all data points into one-dimensional space. But if we want to project original data point into m-dimensional space, we need m vectors. So how can we find these m vectors? So simply, we just take the m eigenvectors u1 to um that having the m largest eigenvalue lambda 1 to lambda m. Okay, so this is what we do in principal component analysis. And principal component analysis involves evaluating the mean and the covariance matrix of the data set, and then finding the m eigenvectors of X corresponding to the m largest eigenvalues. So here are two distributions showing the idea of covariance. For the data like this, we can see that this data would be rather random. So we can say that this data distribution has high variation but low covariance. The covariance means the degree of one variable change according to another variable. Okay, and in this case, the variable x and the variable y seems to be independent. So we say that it's high variance but low covariance. That also means no interdimension dependency. Another example is that the data points are still quite spread, so it's also high variance, and it also has high covariance, because when x become larger, y seems to become larger as well. Okay, and when x become smaller, y also becomes smaller. Okay, so there is high interdimension dependency. And in real world case, many feature vectors, the values in different feature dimensions, have high covariance. So if two dimensions have high covariance, we can simply just store one of them rather than store both of them, because when one value is larger, another one is also larger. If so, we can just store one dimension rather than two. So this is why we can reduce the dimensionality of feature vectors. Another perspective to derive PCA is the minima error formulation. The idea is we want to minimize the projection error, the total projection error from the original data point to the projected data point. So how can we do that? So each data point can be represented by a linear combination of basis vectors. So assume that the original data point is in d-dimensional space. So we have d basis vector, and we can represent each data point as the linear combination of this d basis vector. And now we want to find a subset of this vector so that we have minimal projection error between the original data and the projected data. Okay, and basically, the weight for each vector would be the original data set, uh, the inner product between the original data point and the basis vector. So this is what we say before, like the for this vector 4, 5, 6 can be represented by 4 times 1, 0, 0 plus 5 times 0, 1, 0 plus 6 times 0, 0, 1, right? So this is called analysis. And how can we get the weight for? That is actually the inner product between 4, 5, 6 and 1, 0, 0. Remember that? So here, the weight alpha is actually the inner product between the original data point and the basis vector. So we can rewrite it as this. And our goal is to approximate this data point using a representation involving a restrict number m that is less than d and corresponding to a projection onto a lower dimensional space. So as illustrated in this figure, an original data point xn can be represented by two parts, the summation of two parts. The first part would be the lower dimensional representation, and the second part would be the difference between the original one and the lower dimensional one. So here is the lower dimensional lower dimensional representation, which is actually the linear combination of selected basis vector. And this part is another one. We have the remaining basis vector and uh, doing some linear combination. So we can approximate the data. We can approximate the original data by this one. And this one is the combination of lower dimensional representation and the difference between high dimensional and the low dimensional data. And we want the difference between them should be minimized. So in general, we want to minimize the approximation error, and we can write the approximation error like this. So the difference between original data and approximation data, and and by mathematical derivation, we finally can get the optimal solution is that J is equal to a summation of lambda, where we want to minimize the J, then we want to pick the minimum eigenvalue. So to obtain the minimum value of J, we have to select eigenvectors to those having the d minus m smallest eigenvalues. Okay, we skip the mathematical derivation. Okay, and hence the eigenvectors defining the principal subspace are those corresponding to the m largest eigenvalues. Okay, so this is on the opposite side to view this problem. So we just how can we get the minimal approximation error? We just remove the d minus m smallest uh, eigenvectors, okay, eigenvalues. Okay, we just remove the eigenvectors having the d minus m smallest eigenvalues. So the remaining ones would be the eigenvectors with the m largest eigenvalues. Okay, if you are interested in the mathematical detail, please refer to these two papers. So now we have introduced the PCA, the principal component analysis. So we can describe some application of PCA. So here, assume that we have many images with digit 3. Okay, so given maybe 5 or 10 image consisting of digit 3 in various forms, then we can perform PCA on that. As we said before, the original data would be represented by a 10,000 dimensional feature vector. But now, if we take the average vector, we get this. And if we represent the largest eigenvectors, the eigenvector with the largest eigenvalue, the eigenvector would be like this. The eigenvector corresponding to the second largest eigenvalue would be this, and so on. So here, lambda 1 to lambda 4 are the top 4 eigenvalues. And here we can see some pixels are in blue and some pixels are in yellow. That actually does not represent color. That represent a positive or negative value. Okay. So so these are the mean vectors and the first 4 PCA eigenvectors for the offline digit data set. And we can see that the eigenvalue spectrum from the left to the right is the in this figure, from left to the right is the first eigenvalue, second eigenvalue, third eigenvalue, and so on. And we can see that most of the information concentrate on the first few eigenvalues, as we can see here. So the maybe the fifth eigenvalue is much smaller than the first eigenvalue. That means almost all information concentrate on the first few dimensions. And here is the the approximation error. As we increase the numbers of dimensions to represent the lower dimensional space, the approximation error decrease quickly. So maybe we can just represent the data by 100 dimensional feature vector, so that we have very small approximation error. And of course, if we increase the numbers of basis vector to represent lower dimensional representation, we have a smaller, even smaller approximation error. So here, from both of these two figures, we can see that most of the information concentrate on the lower dimensional, the first few eigenvectors with the largest eigenvalues. So here is the reconstruction result. So given the original image, we can reconstruct the original image based on the eigenvectors. Okay, as we can see that every image can be represented as a linear combination of lower dimensional representation and the projection difference, right? So if we reconstruct these images based on only one eigenvector, then we get the average one. So this one is equal to this one. Okay, and then if we reconstruct based on the 10 largest eigenvalue with the eigenvectors with the 10 largest eigenvalues, then we have reconstruction like this one. We can see that this is more similar to the original data. If we take 50 eigenvectors, we combine 50 eigenvectors, we have even more similar to the original one. And then if we take the if we combine the eigenvectors with the top 250 eigenvalues, we have very good approximation. So this is to say that we don't necessarily represent this image by 10,000 10,000 dimensional feature vector. We can just represent it as a 250 dimensional feature vector. That would be great. Another famous application is eigenface. This is a quite famous application for face recognition. In early years, before 1980s, uh, we don't have good method to do face recognition. In this period, researchers just study the characteristic of our eyes, our nose, or our mouth, and they do face recognition. But that is not effective. Since eigenface was proposed, efficient face recognition system can be built. So the eigenface is a famous application for PCA. So we collect a lot of face image, and then we do PCA. Okay, so here we can see that this is the average face. This is the first eigenvector like corresponding to the largest eigenvalue. This is the second eigenvector. This is the third eigenvector, and so on. And we can project a face on those eigenface. So these are called eigenface. Okay, these are called eigenfaces. And we can project a face onto those eigenfaces to represent face features. So as we say before, we can project a high dimensional face images into a low dimensional space. And in this low dimensional space, the basis vectors are this eigenface. So we can represent a face as a linear combination of this eigenface. Okay, mathematically, we can do so. And how can we compare the similarity between two faces? That is easy because we can project this face image into the low dimensional and represent it as a vector. We can also project this face into low dimensional space and represent it as a vector. Then we can compare them by calculating maybe the Euclidean distance between them. Okay, so this is the main idea of eigenface. And please refer to this paper published in 1991, published in CVPR conference, which is one of the top computer vision conference in the world. Okay. Singular value decomposition, we call it SVD in short, is another important techniques for dimension reduction. SVD works directly on data. So in contrast to PCA, PCA works on covariance matrix of data. Remember that? We just find the eigenvalue and the eigenvectors of the covariance matrix of the data in PCA. But SVD, it works directly on data. The SVD technologies examine the entire set of data and rotate the axis to maximize variance along the first few dimensions. So this is another important dimension reduction technologies. And in the following, we will take this example to explain how SVD works. The data is the document data. So right now we have 7 documents, and assume that in these documents we only have the following words: data, information, retrieval, brand, and alarm. And assume that in the first document we have 1 data word, 1 information, and 1 retrieval word. That means the word data appear once. Okay, and in the second document the word data appear twice, and so on. So here, according to the numbers of or the frequency of each word appear, we may be able to discover the implicit concept in each document. So now we want to solve the following problem. The first one is to find concept in text. The second one is to reduce the dimensionality of each document. And right now, for each document, we use a 5-dimensional vector to represent it. For the first document, we use 1, 1, 1, 0, 0 to represent this document. For the second document, we use 2, 2, 2, 0, 0 to represent this document. And now the goal of this work is to reduce the 5-dimensional vectors into maybe 1-dimensional or 2-dimensional vectors. So how can we do that? So given the data matrix mentioned above, we have the matrix A, which is a m by m matrix. So in this example, we have n document. So we have 7 documents, we have 5 terms. So we are given a 7 by 5 matrix. Okay, so given an n by m matrix, data matrix, we want to decompose this matrix into U, L, V, where U is an m by r matrix. That means the relationship between n document and the r concept. The L is a r by r diagonal matrix, which means the strength of each concept. And usually R is the rank of the matrix. And V is a m by r matrix. That means the relationship between the m term and the r concept. And we want to decompose the matrix A into U, L, V transpose. So here is the example. We are given this 7 by 5 data matrix, and we want to decompose into the multiplication of U, L, V transpose. So here the U is the document to concept similarity matrix. V is the turn to concept similarity matrix, and L is the diagonal matrix storing the strength of each concept. And we want to project. How do we do the projection? How do we project the high dimensional data into low dimensional space? That is, we want to pick the best ASICs to project out. The best means the minimum sum of square projection errors. So we also have this similar concept in PCA. So how can we do that? We can use the singular value decomposition technology we have already studied in linear algebra. So in the previous example, in a given example, we decompose this 7 by 5 matrix into these 3 matrices, the multiplication of these 3 matrices. And here we can see that assume that we already know that there are 2 concepts in the given data set. So we decompose it into a 7 by 2 matrix U, and then 2 by 2 matrix L, and then actually 2 by 5 V transpose. And here the value 0.18 means the similarity between the first document and the first concept. Okay, is 0.18. The similarity between the second document and the CS concept is 0.36, and so on. So here we can see that the first 4 documents have computer science concept. The following 3 documents have medical concepts. For the diagonal matrix, the 9.64 means the strength of computer concept in this data set. Okay, so we can see that relatively we have more document on computer science concept. So here we have higher computer computer science concept. Okay, we have high strength on computer science concept, and we have lower strength, smaller strength on medical concept. For the matrix V transpose, the 0.58 means the similarity between the first term and the computer science concept. So the data has 0.58 similarity to computer science concept, and so on. So we have data, information, retrieval. These three words are related to computer science, and the brain and alarm are related to medical concept. So the question is, how exactly is the dimension reduction done? How can we do dimension reduction? In this case, we can just ignore the concept with smaller strengths. So here we can truncate. We can truncate the singular value here as 0. This will cause the this column to 0 and this row to 0. Okay, so we just set the smallest singular value to 0. That would cause this result. Okay, so all these values can be set to truncate to 0. And then when we reconstruct the original data like this, we will have this reconstruction data. So the first, because right now we have truncate the medical concept. That means we totally ignore the medical concept. So the last three documents are all represented as 0, 0, 0, 0, 0, 0, 0, 0. And the first four documents are represented as 1, 1, 1, 0, 0, 2, 2, 2, 0, 0, 1, 1, 1, 0, 0, and 5, 5, 5, 0, 0. And because the last two dimensions are all zeros, so we can simply reduce the dimension to represent this document. So the first document can be reduced to 1, 1, 1. The second document can be reduced to 2, 2, 2, and so on. And the last three documents can be reduced to 0, 0, 0, 0, 0, 0, 0, 0, 0. So we reduce 5-dimensional vectors into 3-dimensional. So this is how we do dimension reduction based on singular value decomposition. In addition to PCA and SVD, which are variational set method to do dimension reduction, another categories of dimension reduction technology is called multidimensional scaling, or MDS in brief. The goal is to represent data points in some low-dimensional space, such that the distance between points in that space corresponds to the distance between points in the original space. In a word, we want to represent projected data that have similar distance distribution or similar distance relationship to that in the original space. So let's take an example here. So given a matrix where each entry indicate the distance between selected cities in the United States. So right now we have 9 cities, and the distance between Boston and New York is 206 miles, and the distance between Boston and Washington D.C. is 429 miles, and so on. So Given this distance matrix, we want to find a lower dimensional representation where we still can represent, we still can describe the distance relationship between these cities. So from the data set, we know that Boston is close to New York and DC, and it's far from LA and San Francisco. So we also want to have such relationship in the lower dimensional space. So the goal is we can define that we want to map this nine-dimensional feature vector, because right now we represent each city as a nine-dimensional vector. We want to uh, project the nine-dimensional vectors into two-dimensional representation, such that uh, the cities that are close to each other in the high-dimensional space are still close to each other in a lower dimensional space. So here is the example. We can see that the Boston, New York, and Washington D.C. are close, and the distance between LA and San Francisco to Boston is quite far. So we want to find the best low dimensional representation. MDS, what MDS does is to find a set of vectors in p-dimensional space such that the matrix of Euclidean distance among them corresponds as closely as possible to some function of the input matrix according to some criteria function called stress. So here we define the stress function like this. The stress means the degree of correspondence between the distance among points implied by MDS map and the input matrix, and it can be mathematically defined like this. Dij here refers to the distance between points I and j in the original space, and Zij here refers to the distance between point I and point j on the map or on the lower dimensional space. So we want the Dij as closely as possible to the Zij. So we define Dij minus Zij and take square and sum all of them. And after some normalization, we can take the square root. So this is called the stress value. And if the correspondence is higher, that means the distance Dij is close to Zij, then the stress value will be smaller. Okay, so if the correspondence is higher, the stress value is lower. So here is an example showing if we use more dimensions to represent uh, the data point, then the stress value will decrease as the dimension increase. Okay, so the true dimensionality of the data will be revealed by the rate of decline of stress as dimensionality increase. So in this case, we may choose to use three dimensions to represent the low dimensional representation, because the stress value decrease a lot when we use three-dimensional space to represent. If we increase the numbers of dimension to be the low dimensional representation, stress value will also decrease, but the degree of decreasing gets smaller, gets slowly. So how can we find the lower dimensional representation? The algorithm is like here. The algorithm is actually quite simple. Okay, so we just assign points to arbitrary coordinate in p-dimensional space. That means we just randomly assign the position of Boston, of New York, of Washington D.C. in the p-dimensional space. Here p is set to 2 in this case. And then we compute the Euclidean distance between all pairs of points to form a D hat matrix. And then we compare the matrix with the input matrix and evaluating the stress value. The smaller the value, the greater the correspondence. Then we adjust coordinate of each point in the direction that best maximally stress. Okay, so we can just randomly adjust the coordinate of each point and test again, evaluate the overall stress value again. And if it gets better, that means the moving direction is good. And then we repeat the step 2 to 4 again and again until we don't get any lower stress value. So here, this algorithm is quite simple and would be very computational expensive, because right here we just randomly adjust the coordinate of each point. And actually, we have smarter way to adjust the coordinate. And you may learn some technologies from the optimization class. If you take the optimization class, you will learn some smarter ways to do so.
In the following, we introduce two advanced multi-dimensional scaling technology to do dimension reduction. The first one is called ISOmap. That is the abbreviation of isometric feature mapping. And please note that this paper was published in year 2000 and published in Science magazine. We usually know that computer science or computer vision researchers rarely publish their paper in such top-tier scientific journal. So this magazine often publishes the most timely and the most significant scientific contribution to the world. So when this work was published in Science, many people are interested in this technology. So let us start from two examples. The first example is we can capture the head, the statue, from different angle and with different lighting condition and with different lighting direction. So from the left to the right, we can see that we capture this statue from different viewpoint. So here we can see this person's left face, and here we can see this person's right face. And then from bottom to top, that means the up-down pose. So here we capture from the above, from the top of the head, and here we capture the statue from the bottom of the head. Okay, and at the bottom of each figure, we can see a bar indicating the lighting direction. So basically, for the same statue, we can capture various images based on different capturing settings. Another example is the handwritten digit 2. Okay, from the left to the right is the button loop articulation. So this one, from the left one, we don't have button loop, and at the right one we have button loop. And from top to down means the top arch articulation. So at the top we don't have top arch, but at the bottom we have top arch. So again, if we collect many people's handwritten digit 2, we may have various images that all have the same meaning. So we want to reduce the dimensionality to describe such image variation. And to explain the idea of the ISOmap, we start from a synthesized data set. So assume that in the high dimensional space, the synthesized data distribute like this. It's just like a Swiss roll. So if we calculate the distance between this data point and this data point based on Euclidean distance, then we may misunderstand the real distance between these 2 points, because theoretically these 2 data points are apart from this geodesic distance. The so-called geodesic distance is that following the surface of the complex structure, we just can go through the surface of this structure to starting from this point to this point. So the real distance between these 2 points would be this geodesic distance. Okay, so that would be a more appropriate distance measure to show how two data points apart from each other. But how can we estimate the geodesic distance between faraway points? Okay, the idea is we adding up a sequence of short hops between neighboring points. That means we only can jump from this data point to its neighboring data point. Okay, and then we jump to the next neighboring data point, and so on. So with a lot of short hops, we can jump from this data point to this one. Okay, so theoretically, we have a geodesic distance from here to here. So theoretically, it's the distance of the blue line. Okay, but with a lot of short hop, we can approximate this geodesic distance based on this red curve. So how do we estimate the geodesic distance in algorithm? So here is the algorithm. The step 1 is we need to construct a neighborhood graph first. So we will determine which point are neighbors on the manifold. Here, the manifold means the geometric structure in a high dimensional space. Okay, this is a geometric structure. So first we will define what is the neighborhood. Okay, so usually we just define if the distance is less than some predefined threshold, then we say that these 2 data points are neighboring. And then we will connect each point to all points within some fixed radius epsilon. Okay, so here the definition of neighborhood is the data point with the distance to some specific data point less than epsilon, or its k-nearest neighbor. And then step 2 is to so when we determine the neighboring data points, we can construct the neighborhood graph. And then step 2, based on the neighborhood graph, we will compute the shortest path. So we estimate the geodesic distance between all pairs of points on the manifold by computing their shortest path in the graph. Just as we mentioned in previous slide, we will collect a lot of short hops to construct the ray curve path from the source data point to the destination data point. So if we can do so, we can compute the geodesic distance between any 2 data points. So that at step 3, we can construct a d-dimensional embedding. That means we can reduce the dimensionality. The original dimension would be d, capital D, and then we want to reduce the feature dimensions to small d. So that's what we mean in constructing d-dimensional embedding. And then because we already know all distance pair, we already know the distance between any two data points. So then we can apply the MDS technology to the matrix of graph distance and then construct an embedding of the data. So basically the step 3 is the same, exactly the same as what we say before about the multi-dimensional scaling technology. So here are some results of the ISOmap, and we use 4 figures to show the effectiveness. In the first figure, we work on the face image, that is the statue we capture from different angle and different pose and with different lighting condition. And in the figure A, we see that the x-axis is the numbers of dimension we would like to take. Okay, so we map high dimensional space to 1-dimensional, 2-dimensional, or 3-dimensional, 4-dimensional space. And the y-axis means the residual variance. That is actually the projection arrow. You can think about it. And here, the curve with open triangle is PCA. The curve with solid circle is ISOmap. So here we can see that if we map the data into 3-dimensional space, the projection arrow will be largely reduced if we use the ISOmap. And here is the difference between PCA and ISOmap. And remember that we want to minimize the projection arrow. In figure B, we work on the Swiss roll data, okay, which is the synthesized data. So here, if we reduce it into 2-dimensional space, the projection arrow is nearly 0 if we use ISOmap, and the arrow is 0.1 if we use PCA. In figure C, we use another data set, means the hand data set, the hand images, that also have some variation like finger extension and a wrist rotation. So here we also can see the highly effective ISOmap. And figure D is the handwritten digit. And here again the solid circle is ISOmap. The open triangle here is the conventional MDX. The open circle here, the open circle here is the conventional MDS. The open triangle here is PCA. And again, we can see the effectiveness of the ISOmap. And according to the curve, we can determine the numbers of dimensions we want to reduce. For example, here it's obvious that we will select dimension 2. We will select the numbers of dimension is 2. And for figure A, we will select the numbers of dimension 3. For this one, we will select the numbers of dimension 2, because when we increase the numbers of dimension, yes, we will also reduce the projection arrow, but the degree of reduction decrease. So to make some compromise, we may select the numbers of target dimension is 2. The next advanced multi-dimensional scaling technology is called LLE. That is an abbreviation of the locally linear embedding. I forgot to say that actually we don't know the real geometric structure in the high dimensional space. Okay, so this is just a synthesized data for us to understand the idea of LLE and ISOmap. We actually don't really know the real geometric structure of the data point. But we can imagine that the structure in the high dimensional space would be quite complex, and with linear method like PCA or SVD, we cannot appropriately map linearly map the high dimensional vectors into low dimensional space. So this is the idea of ISOmap and LLE. And the work LLE was actually also published in year 2000 Science magazine. Okay, so they basically as the ISOmap, they published in the same issue of the Science magazine. And the idea of LLE is that they try to eliminate the need to estimate pairwise distance between widely separate data points. Because when we have many data points, and if we need to compute pairwise distance, that would be very computational expensive. So the LLE recover global nonlinear structure from locally linear feeds. So the idea is that we also try to unveil or uncover the Swiss roll data, like we just like to uncover this Swiss roll data into a surface. Okay, so the motivation of this work is the same as the ISOmap, but the idea is different. The idea of LLE is that they assume that each data point can be reconstructed by its neighboring data point with a linear combination. So here, the xi, they assume that xi can be described as a linear combination of sj, sk, maybe sp, sq, and so on, with the weighting of sk is wik, the weighting of xj is wij, and so on. And when this data point xi project as yi, so yi is the lower dimensional representation of xi, yk is the low dimensional representation of sk, and so on. They assume that yi can also be linearly reconstructed by yk, yj, yp, yq, and so on, with the same linear coefficient wik, wij. So in a world, they assume that the data point in high dimensional space or low dimensional space can be linearly reconstructed by its neighboring data point with the same linear coefficient. So that's the main idea. So they will characterize the local geometry by linear coefficient that reconstruct each data point from its neighbor. And of course, when we determine the linear coefficient, we try to minimize the reconstruction error. So no matter in the higher dimensional space or low dimensional space, we need to minimize the reconstruction error. And in the low dimensional space, like a d-dimensional space, we also try to minimize the embedding cost. So this is the low dimensional representation, and these are the linear reconstruction based on lower dimensional representation of its neighboring data points. So there are some mathematical mathematical derivation about the LLE. Here we just see an example showing a face. So again, we can capture the face from different angle. We can also have a face that have different expression. So here from the left to the right, if we take from the same viewing angle, that would be from the expression maybe from sad to happy, and then if we go through from this point to this point, we can see that this is sad And then, okay, this is happy. So at the top part, we can see that we capture the human face from his right side. And at the bottom part, we can see that we rather capture the human face from his left part. Okay, so if we map all these face images onto a two-dimensional plane, we can see this distribution that would be quite complex. Okay, but we also can see that because we can well describe the geometric structure based on LLE, so similar data may be mapped onto similar location, just like these two. Okay, and from the left one, from this one, they have similar expression, and so on. So this is why we can apply LLE to get a good mapping result. And if we have good low dimensional representation, low dimensional space, we can more accurately describe the image characteristic. Like we can compute better similarity, we can compute better distance, so that we can achieve better, like better face recognition or better content-based image retrieval. So here are some reference about multi-dimensional indexing structure, multi-dimensional SS method, principal component analysis, and you can refer to the science paper to read about the ISOmap and LLE.